This is a video about the A-level organic chemistry topic of cracking. So just like fractional distillation, you will be familiar with the term cracking from GCSE chemistry. It turns up in the organic chemistry topic in paper 2, but unfortunately, unlike fractional distillation, we're not just going to be able to say, yes, take everything you know from GCSE and just carry it forward. We're going to need to do a little bit of editing. So let's get into it. Before petroleum or unrefined crude oil can be used as a fuel or a chemical feedstock, that mixture gets separated out into fractions. And remember, these fractions are a group of chemicals that have the same boiling point. And because we know that they're pretty much all alkanes, this also means that they're going to have really similar chemistry. So as you can see, there is much greater demand for fuels like petrol and diesel than we can supply using just crude oil, whereas larger fractions like fuel oil have a much greater supply than is actually necessary. So cracking is a process that takes the surplus of fuel oil and other large fractions and allows them to be converted into smaller molecules that are more useful. So at GCSE, you would have learnt that cracking is a type of thermal decomposition, in other words, using heat to break apart a molecule, and that it works by breaking carbon-carbon bonds. So far, so accurate. You would also have explored the idea that conservation of mass or conservation of matter means that the number and type of atoms can't change during a chemical reaction. So when we break apart a large alkane like this decane molecule, we make another alkane like this octane molecule, and we then don't have enough hydrogen atoms left over to make a second alkane. So instead we make this ethane. So you encountered two types of cracking equation at GCSE, and both of these still come up at A-level for a single mark. So in the first example, we've been given one of the products and not the other, and we need to think about conservation of matter. So we think we've got 25 carbons, but then only 10 here. So we're going to have 15 carbons, and then likewise, we've got 52 hydrogen and then only 22 here. So we're going to have 30 hydrogens there. So that's the first example. And then in the second example, we are given both of the products, but we don't know how many of them there are. So in total, we need to add up to have 25 carbons here. So if we take away the 9 that is in that first product there, that gives us 16. And therefore, we know that if we're having ethene as our second product, we're going to need 8 ethene. And I could double check the hydrogen just to make sure I'm right. So I've got 52 here and 20 here. So the difference there is 32, and there's 4 of these. So again, I need 8 of those ethene molecules. So just quickly pause the video and double check that you are on top of these equations. So hopefully you've got carbon 22, hydrogen 44, carbon 17, hydrogen 36, carbon 13, hydrogen 26, carbon 30, hydrogen 62, and carbon 13, hydrogen 28. Rather than just being asked to write down what is produced in the reaction, you might be asked to use a bit of deductive reasoning in a multiple choice question like this one. When octadecane is heated, one molecule decomposes to make an alkane with 10 carbon atoms and 2 different unsaturated compounds. So which of these equations could represent this reaction? Pause the video and see if you can work out what the answer is. So the first important piece of information is that I'm expecting an alkane containing 10 carbon atoms. And I know even from GCSE that alkanes have the formula CnH2n plus 2. So an alkane with 10 carbon atoms would be C10H22. So straight away I can rule out answer B because that doesn't have decane in it, it has decene. Next, it says that I'm also expecting 2 different unsaturated products. So if I look at my remaining equations, if I have some saturated products in there, that's no good. So I'm expecting unsaturated products to probably be CnH2n, but they could also be less than that. So you could, for instance, have CnHn. So straight away I can see that both answers A and answer C have got an extra saturated product in there. I don't have 2 unsaturated products. So that means that my correct answer must be answer D. Now this is where it starts to get slightly more complicated. So at GCSE we said that we were always going to make an alkane and an alkene. So that's a saturated hydrocarbon and an unsaturated hydrocarbon. But there are some other options. So here we've got that same decane molecule, and this time I'm going to break it apart and I'm going to make a butane. So I've got 4 carbons and 10 hydrogens in here. Now this means that I've got 6 carbons left over and 12 hydrogens left over. So I could make some hexene. But the other thing I can do is make this cyclical molecule, and this is called cyclohexane. And because it's formed up into a ring, we don't need that extra hydrogen on either end of the alkane. This molecule still only contains single bonds. So the formula is still the same as I would have expected at GCSE. It's still C6H12, but actually it's not strictly true that we're always going to make an alkane and an alkene, because in this instance we're not making any unsaturated molecules at all. So whereas at GCSE we would have said that we're going to make a smaller alkane and one or more alkenes, we can now get rid of that and say instead we're going to make a molecule that has the general formula CnH2n. Now at GCSE you learnt that that is the formula of the alkenes, so you could have a molecule like this which is unsaturated, but also it could be an aromatic hydrocarbon, so in other words a cyclical ring structure alkane, and that's going to be a saturated molecule, so it wouldn't have any impact on bromine water. So we've said that in order to be an alkene it needs to be an unsaturated hydrocarbon with a double bond. So a hydrocarbon of course is going to have hydrogen and carbon only. Unsaturated means that it's not just single bonds, and then alkene is specifically thinking about a double bond. So if we think about the examples we've got here, our first one is not going to be an alkene because it's not even a hydrocarbon, it's got this bromine atom here. Then our second example we've got over here is actually going to be an alkane. It's not unsaturated, it's only got single bonds. Our third one here is looking slightly more hopeful, but actually if we look at this unsaturated bond here, it's a triple bond, and alkenes don't have triple bonds, they only have double bonds. So this is not an alkene either, even though it is a hydrocarbon and it is unsaturated. But finally we have our ethene molecule here, and this one is an alkene. In your GCSE studies you would have learned that the first 4 alkenes were ethene, propene, butene and pentene. And to some extent this is true. We do use the suffix -ene in order to denote an alkene, and we do use the prefixes eth, prop, but and pent to denote the number of carbons. But although the first 2 of these names are complete, the third and the fourth ones aren't. If you've watched my nomenclature video, then you'll know that we now need to start specifying which carbon the functional group is on. So if I label the carbons that are in this butene molecule, then I'd start with number 1 and number 2 and number 3 and number 4. And so this double bond is between carbon 1 and carbon 2, and I'm always going to use the smallest possible number. So this is but-1-ene. If I do the same thing with the next molecule, then I can see that the carbon-carbon double bond is between carbons 2 and 3. So this is but-2-ene. But it might surprise you to hear that this next molecule is also but-1-ene. And the reason for this is that we are always trying to use the smallest possible number, and we can label from the left or the right. So if I label from the right hand side, then we have carbon 1, carbon 2, carbon 3, and that double bond is still between carbon 1 and carbon 2. So therefore this is but-1-ene, not but-3-ene. You should also be aware that we're only going to use numbers when they're actually giving us additional information. So this here is going to be propene. It's not going to be prop-1-ene because even if I redrew it with the double bond on the other side, then I would still just start counting from the other end of the molecule. So even though this is a mirror image, this would still be prop-1-ene, for want of a better word, because I would just start labelling my carbons there. So there's no point in calling it prop-1-ene because prop-2-ene wouldn't exist. So in that instance, we just don't include a number. So for both propene and ethene, you shouldn't have any numbering in your name. As you learnt at GCSE, we can test for the presence of unsaturated bonds by using bromine water. So bromine water is orange, and it remains orange in the presence of alkanes or cycloalkanes as well, but it turns colourless when in the presence of a double or triple bond. So now for the frustrating bit. And I'm going to preface this by saying that although at GCSE we learn about 2 types of cracking, and at A-level we learn about 2 types of cracking, actually there are loads of different types of cracking. And the particular type you're doing and the reaction conditions you're using are dependent on the product that you're particularly interested in making. So are you wanting alkenes for making plastics? Are you wanting aromatic hydrocarbons? What is it you're trying to achieve? So the irony is that at GCSE we kind of mixed and matched some different types, and you'll see what I mean in a second. But I would strongly suggest that you just put everything you know about reaction conditions for cracking from GCSE to one side and start from scratch. So our first type of cracking, and this is the one that we did talk about at GCSE, is catalytic cracking. So catalytic cracking, technically speaking, does involve slightly elevated pressure. So atmospheric pressure in the room with you right now is about 100 kilopascals. Industrially, they're going to use about 200 kilopascals, so about 2 times the normal atmospheric pressure. So we can kind of fake it in a GCSE school lab, but it doesn't work as well as it works if it's got slightly increased pressure. It uses a reasonably high temperature, so 600 degrees Kelvin, that's about 330 degrees C. You can definitely achieve that with a Bunsen burner. And we use something called a zeolite catalyst, so that's aluminosilicate or aluminium oxide. That is the catalyst that you would have used if you did this practical at GCSE. You just probably wouldn't have been told that, but you now do need to know that name, zeolite. And ironically, given that at GCSE we told you that cracking was going to produce alkenes, catalytic cracking tends not to. It mainly tends to produce the motor fuels, so those are our short alkanes, and aromatic hydrocarbons, so those are the ring-shaped hydrocarbons. And then the second type of cracking that you need to know about is thermal cracking, which we didn't cover at GCSE. And that might be a bit of a confusing statement because you're thinking, hang on, but we said that cracking was thermal decomposition, so surely that is what it is. But the cracking that you did at GCSE, whether it was with a zeolite catalyst or with steam, that was all catalytic cracking. And the reason I know that it wasn't thermal cracking is that I guarantee you that you could not produce a pressure of 70 atmospheres in your school laboratory. You're just not going to be able to do it. So thermal cracking, when it's done in the industry, has this really high pressure. It's about 70 times higher than atmospheric pressure, and also a high temperature. So from slightly higher than catalytic cracking right the way up to about 1200 degrees Kelvin, which is way hotter than you could produce in your school laboratory. And thermal cracking is going to produce a high percentage of alkenes, so that's very useful if you're trying to make plastics, and also sometimes some hydrogen. So let's finish off with a multiple choice question. Which of these statements is correct about catalytic cracking? A temperature between 450 degrees C and 750 degrees C is used. Alkenes are the major products. Carbon-carbon bonds are broken. Or platinum catalysts are used. Pause the video, scribble down what you think the answer is, and then we'll go through it. So a temperature of 450 to 750 degrees C, that's not going to be catalytic cracking, that's going to be thermal cracking. Likewise, majority alkenes, that's going to be thermal cracking as well. Platinum catalysts are used in vehicle emissions. For catalytic cracking, we're going to want a zeolite catalyst. So the correct answer is that the carbon-carbon bonds are broken. Thank you very much for watching, and I hope that you found this video useful in your A-level chemistry studies. If you did find it useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.